Let's go. So we're going to do 3 examples of Gaussian elimination here. Right. So the first step is to put the matrix in what's called augmented form. You kind of just forget about the x and y and just note that you have a first variable and a second variable. So if we do that, we get 1x, 2y equal to 2. And we get 2x minus 1y equal to 1. Now what we're going to try and go for is we want to get this in the form 1, 0, 1, and then the rest of it doesn't really matter. Okay, so we have a pivot in the top left corner, so that's great. So what we're going to do now is we're going to try and get this 0. So what we're going to do is we're going to do row 2, send to itself. Now you can't do take away 2 to make a 0 because that's not a row operation, but you can use the pivot in row 1 and you can do row 2 minus twice row 1. Now the first row remains, and now you do row 2 minus twice row 1. So you do 2 minus twice 1 is equal to 2 minus 2 is equal to 0. Minus 1 minus twice minus 2 is minus 1 minus 4 is minus 5. And then 1 minus twice 2 is equal to 1 minus 4, which is equal to minus 3. So now what we have is we have our pivot, and we have our 0 underneath. We want to turn that, now I'm tired, I might make silly mistakes in these, no mathematical ones, just little slips. I want to turn the minus 5 into a 0, into a 1, because I want another pivot. So how I turn the minus 5 into a 1 is I divide by minus 5, which is a row operation. So you send row 2 to itself divided by minus 5. Now, some people are looking at it, might be thinking, oh, there's an alternative. How about at this point, see what I could do, how could I turn a minus 5 into a 1? I could add 6. So why don't I do row 2, send to itself, and I can add 6 by adding 3 times row 1. And the reason I don't do that is because that would mess up this 0. Because while it would get the 1 I want, I would also have 0 plus 3 times 1, I'd get a 3. And I want a 0 here. So what you're doing is you're making pivots and using the pivot to kill everything underneath. And you make the pivot using division. Now sometimes there are shortcuts that do work, but this is one that doesn't work. Okay, we're going to do the row 2 divided by minus 5. So we get first row is sound, 1, 2, 2. And then the second row, so 0 divided by minus 5 is 0. Minus 5 divided by minus 5 is 1. And minus 3 divided by minus 5, minus 3 divided by minus 5 is 3/5. Now I'm going to just check the next page to see where I'm going with the space here. So we just work here. So we've got our pivots. There are solutions because there's nothing of the form 0, 0, 0, non-zero. So I just say solutions, yes. And are there any pivotless columns? No. So that means there's no parameters. There's a unique solution. And let's find it. So the second row says 1y is equal to 3/5. And the first row says 1x plus 2y is equal to 2. We have already found that y is equal to 3/5. So you got x plus 2 times 3/5 is equal to 2. And that's 6/5. So if I take away 6/5 from both sides, I get that x is equal to 2 minus 6/5, which is 4/5. And so I have an answer. X is 4/5 and y is 3/5. Now, a completely obvious thing for you to do in your assignments and when you're doing exercises is check your answer. So take these and sub them in. Now I have to warn you, you need to check both of them, not just one of them. Like y could be wrong, and if y is wrong, notice that you've got the same equation, x plus 2y equal to 2. So you could put in y equal to 598 and you'll find a value of x that makes that work. Do you know what I mean? So what you do is just check both of them. So like if I check the first one, I get 4/5 plus 6/5 is 10/5, which is 2, correct? And 8/5 minus 3/5 is 1, that's correct. So this is, so I can check my answer basically, which is nice. Right. Next example. Oh, here we see a picture, right? So so x plus 2, yeah, let me see. So let's just dwell a second on these. So we have two lines. The first line is given as x plus 2y equal to 2. And the second line is given, well, it's just an equation at the moment, 2x minus y equal to 1. I got them from the previous page. I have another screen marking I'm using. So if you want to sketch these things, they are lines, you solve them for y. So the first one, to solve for y, you could take away x from both sides and you get 2y is equal to minus x plus 2. And then divide both sides by 2, you get y is equal to, now minus x divided by 2 is the same, so minus x divided by 2 is the same as minus a half x. I'm happy with that. So you can think of the minus x as minus 1 times x. So divide that by 2, you get minus 1 over 2 times x. And then 2 divided by 2 is 1. And then we'll do similar for the other one. It's a bit easier. We'll just go a bit quicker on this one by adding y to both sides and taking away 1 from both sides. So get y is equal to 2x minus 1. Now we have a little bit of theory that says if you've got an equation of the form y equal to mx plus c, it is a line, m is the slope, and c is the y-intercept. I think you would have done a bit of this with the curve fitting last semester. So if I look at this line here, look, it's cutting at minus 1, and it's got a positive slope. Now the slope is 2, but I'm just gonna say it's positive. And the other one, look, that cuts at 1, and the slope is minus a half, which is negative. And you can see that they have a unique solution. And in fact, if one of the slopes is positive and one of them is negative, they'll have to have a unique solution. If they have the same slope, there's two possibilities. Either the lines are different, in which case they're like parallel and there is no intersection, or the lines are actually the same line, in which case there's infinitely many. Okay. Right, next one. Now, we met this exact problem and we made a mess of it. We got the answers totally all over the shop. Like the answers should be kind of close, both close to 1, and I think we got something like 0 and 1. So if we're doing 4-digit rounding, we have to be, if we're doing Gaussian elimination, and you absolutely have to round like as if pretend you're a computer, you have to do partial pivoting. So what partial pivoting means is you do not want to divide by a small number. That's a problem. So what you need to do first is, now we'll just write it in augmented form first. This is deja vu. So we solved this, we made a mess of it. Now we're going to get things right. So the pivot in the first column, now this isn't actually a pivot yet, but the when I say pivot, I mean this yoke is small. You do not want to divide by a small number. So what you're going to do is you're going to swap row 1 and row 2. And if you do that, you're going to divide, instead of dividing by a very, very small number, you're going to divide by a relatively bigger number. You're not going to see the problems that we saw before. So if we swap them, swapping row 1 and row 2, we'll get 0.4 minus 0.3, 0.1, and 0.0001. And if you do this, you're not going to divide by that small number. And in fact, that 0.0001 is going to be treated a bit more like 0, which is a bit more like what you want. It'll kind of come out in the wash that if you do it this way, it'll be treated like 0. Yeah, so we want to turn that 0.4 into a 1. So I'm going to do row 1 divided by 0.4. So 0.4 divided by 0.4 is 1. Minus 0.3 divided by 0.4 is minus 0.75. Now I've only got 4 significant figures. I mightn't actually need them here. 0.1 divided by 0.4, if I go on a calculator, it would be 0.25. Okay. And now what I want to do is I want to turn underneath the 1 to be a 0. So I need to kill the 0.0001. So how I'm going to do that is I'm going to do row 2, send to itself, take away 0.0001 times the new row 1. So I'm going to use the pivot to kill this thing. So I've got that small number minus that small number times 1 is the small number minus the small number is 0. Now I'll go into the calculator. 0.5 minus 0.0001 by minus 0.75. And to 4 significant figures, it comes out as 0.5. So it's 3 zeros, 4 zeros, 3 zeros, and a 7. So 1, 2, and the third 0, because it's 0, 7, rounds up to 1. And we'll do the same crack with the other one, which would be 0.5. So this is the last thing, minus 0.5 minus 0.0001 times 0.25, and it comes out as 0.4. And I have 3 9s, but it's a 7, so that means that it's 9, 7 that rounds up, and I end up getting 0.5000. Now I want to get another pivot. So what I have to do is to turn the 0.5001 into a 1, I need to divide by that number. So I'm going to send row 2 to itself divided by 0.5001. And so we get first row is 1 minus 0.75, 0.25. 0 divided by that number is 0. 0.5001 divided by 0.5001 is just 1. And then we're left with 0.5000 divided by 0.5001, which comes out as 3 9s and an 8, and then a couple of zeros. So to 4 significant figures, we're getting this. Now look where we are. Pivot, pivot. There are solutions. Now, in fact, if there's rounding, there's going to kind of have to be unique solutions. Well, you're going to hope so, because like if you're rounding, like there's something very precise about having infinitely many solutions or no solutions. It's like the usual situation is you've unique. So if you've no solutions, genuinely, if you move a tiny bit away, so change one of the numbers only slightly, you'll probably have solutions. And similarly, if you've no solutions and you change one of the numbers very, very slightly, the odds are you'll have a unique solution. So usually if there's rounding involved, there will be unique solutions. So let's go. The second equation here reads 1y is equal to 0.9998. Last time we got 1, I think. And x minus 0.75 times y, I'm going to write in the y now, 0.9998 is equal to 0.25. Now to find x, all I have to do is add that 0.75 by that 0.9998 to both sides, and I get 0.25 plus 0.75 by 0.9998. Sorry, that should be plus, shouldn't it? Sorry, add to both sides. So I end up with 0. I get 3 9s and then an 8, but then a 5. So it's 9, 9, 9. I have an 8, but it's a 5, so it rounds up. So I get answers of x is 0.9999 and y is 0.9998, and they're very accurate. And if we look at it down below, there's a small error in x in the fourth significant figure. Y is correct to 4 significant figures, but when I didn't swap the rows and did the same amount of precision, the same amount of rounding, I got answers of 0 and 1, which were miles off. Okay. Now, hopefully in this final example of the week, we can maybe understand a little bit about where parameters come in. Now, I have a design problem. Now, there might be a small mistake in this. I can't remember. I probably won't. Okay, we'll just have a look. So consider we have a design problem on the next page. We're going to have a rectangular perimeter wall to be built at a cost of €100 per meter. I don't know if that's realistic or not. Don't ask me. Inside the perimeter, an enclosure is to be built of the walls. Okay, here we go. So there's different costs going around. Everything's supposed to cost 5,400. The length of the outer perimeter is supposed to be 60. The perimeter of the three-sided enclosed wall. So I think the enclosed wall is more expensive. So this bit is €200 per meter. And this wall is €100 per meter. Okay. And the total cost is to be €5,400. Now, if you think about it, what would be more realistic is that you want the cost to be less than that, and that's you move into something called linear programming, which isn't to do with computers at all. But that's I don't know. Do you do some of that if you go into Forger of level 8? I don't know. Anyway, we're going to do it so that the job costs exactly €5,400. The perimeter is to be 60 meters, so the whole way around is 60 meters, and the three sides of the enclosed wall is to be 24 meters. And so we've defined these lengths. Length 1 is the long length, according to the picture. Length 2 is the short length, and length 3 is kind of the width of that region. It can be shown now. It might be worth checking these. We might just check them briefly there, just because what I want to do is maybe do the problem and then look at the solution to kind of help you understand where the parameters are coming from. But if the answers don't make sense, it won't work, because I think there was an issue with this. So this one does make sense, because if you do the length of 1 plus length of 2 plus length of 1 plus length of 2, that's the full perimeter, should be 60 meters. Divide both sides by 2, you get that. The second equation looks like it might be an equation in money. So let's write down the equation in money. So you've got 2 outside walls. So that'd be like 2L, the L1 and the L2. Let's say, so 2L1 plus the 2L2, that's the length of the wall, times €100 per meter. Now this is an example where there's a relationship now between the first equation and the second one, because you could replace the 2 length 1 plus 2 length 2 with the number 60. So it looks like we've 3 equations, but we actually don't. So that's that bit, plus the other bit. So how long is this interior bit? So it looks like you've got 2 of these bits, and these are length 2 minus length 3. Sorry, excuse me. And they cost €200. And you have this little one here, this length. Now this length is length 1 take away 2 L3s. So plus length 1 take away 2 L3s. Now if the numbers here are wrong, we're not going to worry about it. And this is an equation in money, so this equals 5,400. I can divide both sides by 100. I get rid of that, and that. And then I just want to check have I got the right equation. So how many L1s have I got? I see 2L1 plus 2L1. So straight away I see it should be 4L1. Yeah, so there might be an issue with this. So apologies about this. So the equations aren't correct, but if you form them, so we'll talk loosely rather than putting in numbers. Okay, apologies about this, but we better just drive on now. Is there something else going on? No, we better drive on. Okay, so let's just solve this linear system. And then the question is, does the design specification specify all dimensions uniquely? So in other words, is there only one possible set of values for length 1, length 2, and length 3 that does this? Now, basically, the idea is we're going to see infinitely many solutions. Now, their solutions are wrong for the problem, but look, so one way you can do it is if you, so I'll just kind of show you things that'll have the same thing. So you can make it something like this. That's one extreme, and the other extreme is something like this. So I think these they have the same perimeter. Yeah. Maybe the picture in here isn't quite right. Because remember, the perimeter of this must be fixed. So maybe you get something more like that. Something like that. So in this one, this looks like it's not well drawn, but this might be a bigger value of L3 or something. Look, we better just do the maths. But basically the story is there's loads of different ways that this can happen. So if you give these specifications, it doesn't uniquely identify the solution. And that'll all come out in the wash. So first of all, put the matrix in augmented form. So the first equation reads 1L1, 1L2, 0L3 equal to 30. The second equation reads 2L1 plus 3L2 minus 4L3 is equal to 54. And the final one reads 1L1 plus 2L2 minus 4L3 is equal to 24. And we've a good start made here because we have already got a pivot. Okay, so what we need to do now is turn the things underneath the pivot into zeros. So we're going to do that using the pivot. So we're going to do row 2 is sent to itself minus twice row 1. That will kill the 2. And we'll do row 3 sent to itself minus row 1. So we'll always use the pivot, the big 1 there, to kill the things underneath. So if we do those things, so I get 1, 1, 0, 30. And then let's look at row 2. So it's 2 minus twice 1. 2 minus 2 is 0. 3 minus twice 1. 3 minus 2 is 1. Minus 4 minus twice 0 is minus 4 minus 0 is minus 4. And 54 minus twice 30 is 54 minus 60, which is minus 6. Now let's see the next one. Row 3 minus row 1. 1 minus 1 is 0. 2 minus 1 is 1. Minus 4 minus 0 is minus 4. And finally 24 minus 30 is minus 6. And here we see it looked like we had 3 equations, but actually we only had 2. Because we have got this relationship between row 2 and row 3 in particular, they're the same thing. Pivot, pivot. Use this second pivot now to kill off the thing underneath. We're going to do row 3 is sent to itself minus row 2. And so we end up then with row 1 is sound, 1, 1, 0, 30. Row 2 is sound, 0, 1, minus 4, minus 6. And now let's look at the last one. Row 3 minus row 2. 0 minus 0 is 0. 1 minus 1 is 0. Minus 4 minus minus 4 is 0. And minus 6 minus minus 6 is 0 as well. And so what we have here, pivot, pivot, staircase, we're done. There's no row of the form 0, 0, 0, non-zero. So the bottom row in particular is fine. So there are solutions. Now, if you look at the column for L3, there's no pivot there. That means that L3 can be any value at all. So we say that L3 can be any real number. Now it'll have to be a positive real number because it's a length, but we won't worry too much about that. So now we go to the second last row, which says that L2 minus 4L3 is equal to minus 6. And we know that L3 is equal to T. So this is a minus 4T. So if we add 4T to both sides, we get L2 is equal to 4T minus 6. So we have L2 in terms of T. And then let's look at row 1, which says that L1 plus L2 is equal to 30. And we know that L2 is equal to 4T minus 6. And we can add the 6 to both sides and take away the 4T to find that L1 is equal to 30 plus 6 is 36. Take away the 4T from both sides, we get that. So what we find is L3 can be anything. Now there's the other values, yeah, we can't get into it because unfortunately there's a mistake with the equations, but if we analyze it, there's some mistake with the equations. But anyway, so different values of T give you different solutions. So it corresponds, you get different shapes. So this might be maybe a large T, excuse me, yeah, a large L3. So this is T large maybe. That doesn't, even the pictures don't make sense. But anyway, you can make this region wider or narrower and you get different solutions. So what is the question there at the end? Do the design specifications specify all dimensions uniquely? No, as there are infinitely many solutions. Okay, so that's our first week of lectures.